Hello everyone, welcome back to this series. In this video, we'll focus on analyzing the electrical performance of our 24 GHz microstrip filter using S parameters. We'll also start tuning key design parameters to see how they impact the filter response. This is where the design becomes interactive and you start building intuition about how geometry will affect the performance of your circuit. So I'm gonna first start by creating a new graph. So I'm gonna go to graph, right click, new graph, and then here I'm gonna specify the name for this graph. I'm gonna specify measured versus closed form. And then I need to specify the type below. It's gonna be a rectangular graph, and then I'm gonna click on create. Now over here, I need to add my measurements. So I can right click on my graph, add new measurements. I'm gonna specify an S parameter simulation, and then I need to specify my data source. In this case, it will be my circuit schematic. I'm gonna start by the return loss, which is my S11 parameter, and then I want to add my insertion loss, which is my S21 parameter, and add them to my plot. Now, if it happens the circuit was not simulated, you can go to simulate and then analyze to run your simulation. These two parameters will give us a clear view of how the filter is behaving across multiple frequencies. Next, let's add markers to better analyze the response. So to do this, we can right-click on the graph and select Add Markers, then choose the trace where we want to add the marker and select a specific point. Once the marker is placed, you can move it along the trace to inspect values at different frequencies as well. Another thing we can do is we can match the color of our marker to our trace. And to do this, we right click and then go to the options section. And in the markers section, we need to enable the match text color to trace option and then click on OK. And now you can see the color of our marker is the same as the color of our trace. Alternatively, we can use the Ctrl+M shortcut key to add another marker. Now, adding markers is especially useful for identifying center frequency, the bandwidth, as well as loss at specific points if needed to. At this point, your simulation result should resemble the expected bandpass response. So you have a peak in S21 around 23 GHz and a good return loss within the passband. This confirms that the initial design is behaving as intended. Now comes the important part, and that is tuning. So we're gonna tune my parameters that are in my dimensions box over here. And there's two ways to specify parameters for tuning. I can first open my variable browser window and enable the tune column next to the parameter that I want to tune. Another way, let's close this window, is to use my tune tool over here and select my parameters that I want to tune, and they turned into blue. Now let's open my tune table. Over here, I have a list of all of my tunable parameters with their lower and upper size. So I can specify a range for my parameters and their step size as well. Now that we specified the upper and the lower limit, I'm gonna click on Windows and tile vertical to see both my schematic and my graphs. And now I can start using my tune slider over here to change the values for my parameters. And as you vary these values, observe how the response changes as well. And pay close attention to how each parameter affects the filter. Some parameters will shift the center frequency, others will affect the bandwidth, and some influence matching and return loss. This process will help you understand the sensitivity of the design, and instead of just accepting a response, you're actively shaping it. Now in the next video, we'll import measured data and compare it directly with this electrical simulation to see how close our design is to reality.